There, now it's recording.
All right, so we figured out L1, L2 slash neutral, just depending on what we're using it for, and ground. We're all okay with this, right, so far? Right. So, ground shared between the two of them, okay, it's used for the computers, it's used as electrical ground, fine, whatever. We've got to figure out what our control pilot and our proximity pilot are. So I put them down as CP and PP. All right, yeah, I heard the chuckle. So the control pilot, if you're in control, you make the negotiation, right? At level 1 and 2 on this system, the control pilot is a PWM signal, and it is generated by or from EVSE. Okay? And it's going to pulse up and down and up and down and up and down and up and down, kind of like that. And that pulse width will change the percentage of on versus off time in order for the EVSE to tell the car how many volts are available. This is based on a 12-volt circuit. 12-volt circuit. And the signal goes from EVSE into the vehicle. All right? I'll get into the changes that it makes here in just a second. But we've got a 12-volt PWM signal coming out of EVSE, goes through a few resistors. It can tell whether or not it's hooked up to the vehicle by the resistors that it goes through. I'll put the diagram up on the board in just a second. Okay. The control pilot, responsible for determining the current that is going to go into the vehicle. Determine the charge rate between the EVSE and the vehicle. If the vehicle can charge really high, but the EVSE can't charge really high, the EVSE tells the vehicle, I can't go that fast, and the vehicle has to conform. Or the EVSE says, I can charge really fast, but the vehicle is almost full, so it can work underneath that really fast rating. Okay, that's all that's going on there. I can charge really fast, I can charge really slow. A PWM signal works up until 80 amps. After that, this changes to a PLC signal, power line communications. I'll put the slides up and we'll talk a bit in a minute. Okay. The other one is a proximity pilot. Proximity pilot is not a PWM signal. Instead, it is a DC signal. And instead of coming from the EVSE, that proximity pilot signal goes to the EVSE. It comes from the vehicle. And instead of being a 12-volt source, this one is a 5-volt source. Just like that. Proximity pilot is simply there, in most cases, to ensure that a vehicle is connected before turning on L1, L2, or the DC pins. The control pilot and the proximity pilot both have to talk in order to charge. It's a redundancy circuit. Just in case, you know? Just in case. How do we like that? Take a photo of that, because I'm going to remove it from the board. We got charging levels we did, charger versus EVSE, working on that, haven't done that, working on that, charger operation we did. Everyone got their photo? All right, here we go. all that hard work, all that art. However, you weren't here, this just looks like scribbles. Probably still looks like scribbles, I just make sense of it in my head. That because I'm going to do this. And then I go like this. Oh, and now it's nap time. So there's your whole charging system, onboard charger right there, all drawn out for you, right? And after this, the next few slides in the deck actually are just little descriptions on how everything in it works, okay? So we got into rectifiers, PFCs, look at that. Oh, some DC converters. This is what I want. All right. That's level 3. I don't want level 3, I want level 2. There we go. All right, there's the circuit I want. This guy here is the communication circuit for the control pilot. What does the control pilot do again? What does the control pilot do? That's right, it negotiates a charge rate. So what does it do? Everybody, for the exam, negotiates a charge rate. All right, where does the signal originate from? The EVSE, that's right. You guys are good. So here's the EVSE here. Here's our connection. Our control pilot is pin number. And that means our ground is pin number 3. Power, when applied, when we first connected, it's 12 volts, steady state. Steady means it's just up high. We plugged in an oscilloscope. Just sits at 12 volts. When we plug it in, click, click, the car can see that it's plugged in. However, because we go across this resistor, what happens between here and here on a resistive circuit if it's connected? Did the voltage drop? If we go across a resistor in an active circuit, does voltage drop? What does a resistor do? Consumes power, turns into heat, true? And in this circuit right now, I'm going over a resistor, going along, going along, going along, can it flow through the diode? Diode's in an arrow, it's going forward, can it flow through? Somebody's got to give me an answer. I'm talking to myself here. It's starting to hurt my feelings. What are you going to guess? What tune are we listening to right now? None? Oh. Can we go through a diode in forward bias? Forward bias. We can keep going. Okay, so we go through the diode. Can it go through this resistor? Hold on. Connects way over here to ground. Can it go through it? Sure can, right? So it can go through this resistor. That resistor, something's going to happen there. It's going to go through just like so. This second resistor over here right now, with the car just being plugged in and going, yo, what's up? This switch is open, so no, it cannot go through here. And it sees a buffer here. Oh, mint. Okay, so the buffer can go that way, but the resistance in the computer is super high. So its two main current drops, or sorry, its main two voltage drops are here and here. After my last resistance, how many volts are left? 0, true? So at the end of the circuit, my total voltage should be 0. So here I got 0 volts. In this configuration, between here and here, roughly 9 volts. Hold on, let me double check. Wouldn't want to tell you wrong. We're going to turn it on first. 9 volts, look at that, eh? See that? It's like I remember from a chart. So we got 9 volts. Does the EVSE see the 9 volts? Let's see. So there's an eyeball right here. There it is. It's looking at that wire. That wire is after R1. Does it see 9 volts? Yeah, it has to, right? So it sees 9 volts and it says, you know what we're going to do? We're going to go off 12 volts solid state. And it goes on to pulse width modulation. So now it varies the frequency or varies the pulse width. Dot, 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 dot. So state A, 12 volts solid, measured at the EVSE. Car is disconnected. State B, 9 volts solid. Once it sees 9 volts solid, it knows that it can start telling the car how many amps it can put out. So it goes from solid state to pulsing. State C. Everything's good, everything's good, everything's good. Is the vehicle charging yet? No. No. What the vehicle is going to do, it's going to create a parallel circuit down here by closing this switch. When we close the switch, now we've got 2 resistors in parallel. What does a parallel circuit do to my resistance? If I have 2 resistors in parallel or 1 resistor in series, and they're all the same value, 2 parallel resistors that are the same value, and 1 resistor that is the same value. So, you know, as an example, we go, there we go, we got This is 1 ohm. This is 1 ohm. Or we put a series circuit in, and this guy is 1 ohm. So RT equals 1 ohm. On this one, RT equals what? RT equals what? Want to see 2 ohms? I'll show you 2 ohms. There. Put it another way. Man, we're going back to basics here like this. So you're out and about like a rainbow trout, as we tend to do. Okay? Ugly lights are coming on, it's about to get out. So you're out and about like a rainbow trout. You decide, today's the day I'm going to invest in my career. Where do we go? I need some tools. Where do we go? It's Sunday. Where do we go? You got it. So we got, and it's got the leaf in it, right? What is that? It's like this now. Yeah, I'm trying to draw a pot leaf. It's not going well. There we go. There, I'm in. It's Canadian Tire, non-branded Canadian Tire. We'll call it Toronto Tire, just so we don't get in trouble, right? Man. Okay. So, we're at the Toronto Tire store. And man, here we are. See us in the back of the store? We have a shiny new wrench. There it is. Look at that, eh? Oh, yeah. Where do I want to go? And of course, it's got to have a wing on because it's a cool hatchback. There we go. Got a little ground effects going on here. Time trialing. Right? Wicked like an EK Civic or something, right? Super awesome. Golf R. Heavy in the R. Okay? It's right there in the parking lot, right? That's our ground. That's where we want to be. The problem is, it's two people who joined there. Okay, we got all those people. And right at the front here, we got where we gotta go. We're not shoplifting the wrench just to get through faster, okay? That's a short circuit. We don't want a short circuit. Make sense? So at the front, we got our conveyor here. This is the first time I've ever drawn this with perspective. Look at that, eh? And then of course, we have old Mary here, that's a set of glasses we're going to draw the thing on. She's got some curlers in her hair, all that kind of stuff. She got a job just to get out of the house, right? Retired, but not quite enough money to retire. You all know the type. Okay? How dedicated is she to getting you through pretty quick? It's a retirement job, Sunday staff, they don't want to be there. You're at the back of the store. How quickly is that conveyor moving? Pretty slow, right? Like, I mean stupid slow. So we're going to say 1 customer per minute. You got to go fix something at home. That's voltage, that's pressure, right? And the current right now, it's not great, right? So there's 1 minute, 2 minutes, 3 minutes, 4 minutes, 5 minutes, 6 minutes, 7, 8, 9, 10, 11 minutes in line. Plus you, that's 12 minutes to get out of the store. She's a resistance, right? Jesus, Mary, what are you doing? So, you know what we do? Sean from Lumber to Cash, please. Sean from Lumber to Cash, right? So Sean shows up. Sean's got his safety goggles on. There we go. Strap happening here. For some reason, Sean's got buck teeth. There we go. And he shows up. He's not real good either. He's got a bald head for whatever reason. Quality challenge. We got the conveyor here. Now Sean is about as good as Mary. He's 1 customer per minute. Are they operating in parallel? People can go to 1 or 2, right? Is Mary passing any more people per minute? No, it's 1 per minute, right? How many people get through the till every minute? 1 plus 2, right? Because I have 2 resistances that are the exact same in parallel. So my resistance, or the time it's going to take me to go outside, has been cut in half. So my resistance is higher or lower? It's lower, right? Back to here, that resistance is lower. So it means that more voltage gets used up at this roadblock because I have a parallel circuit. Right? More pressure gets used up here. This is the guy back here, you know, the big first pressure. Making sure that you're social distancing, or can I check your backpack when you walk into the store? That's your first resistance right there. Your second resistance is the 2 cashiers trying to let you out of the store after you paid for your stuff. Why are you giggling like you didn't pay for your stuff? Pay for your stuff, man. Okay? Unless it's a big corporation, then I don't care. So, what did that do to our voltage? The red voltage in between our first resistance and our second set of resistances, it means more voltage got used up here. So now, once we close switch 2, 6 volts, and it's pulsing. 6 volts and pulsing tells me that the car has told the OBC, I'm ready, baby, I'm going to start charging now. 9 volts with a pulse, they're negotiating. 6 volts with pulse, they're charging. Okay? Cool. Do you have to remember these signals and resistor values going forward in your life? Like, you know what, that fat guy wasted like a half hour of my time talking about this crap. Do you have to store these values in your head, 12, 9, 6? No. Where can you store them? If you're on this page, look right below it. There's a whole chart of the values and what they mean. Was I right? Was it 6 volts is charging? So 6 volts, pulse width modulation, vehicle connected ready, EVSE ready, no area ventilation required. It's charging. Bam. Isn't that crazy? Then 3 volts. 3 volts is a different resistance if it requires area ventilation. Does a lithium battery require ventilation? Does a lithium battery off gas when it is charging? Is there a spot in the little plastic baggie that the cells are stored in a pouch for it to vent out? Or are they sealed? They're sealed, right? Venting is not required on all of our lithium stuff. So, 6 volts. Bam, just like that. Now, this only works for level 1, level 2. We'll get to level 3 in a minute. I know you're chomping a bit for it. Look at these. Anybody watch Trailer Park Boys? You watch that? No? Bottle Kids? No? Oh, bad reference then. Bad reference. You know what Bottle Kids are, yeah? Good. Goddamn Bottle Kids. Okay. So the Bottle Kids in that show are a bunch of kids that run around the neighborhood causing chaos by throwing glass bottles. Or you drive by, they throw glass bottles at your car. It's a trailer park thing. I don't make the rules. I just follow them. Okay, so kids in chaos. How's that? We're giving kids in chaos? Here we go. Oh, not that. Not that. That! Proximity pilot. Okay, so we just did the control pilot, we have the proximity pilot. Where did my source come from when we did proximity, or when we did control? Came from the EVSE, so the signal went out from here. Now, we're going to screw it up. We're going to go from 12 volts down to 5 volts. And of course, the car is going to detect how many volts it has right after a resistor, so it's looking at voltage. Okay? When I'm unplugged and I got nothing here, so from here over is missing. Cross it, cross it. Is there a complete circuit here? Does that look complete? Comes down through here, goes back up, goes through here, goes down, he goes through. Does that look like a complete circuit? It's not a trick question. 2 resistors in series that have a ground path and a voltage source. Is that a complete circuit? Sure is. So, 2.7 thousand ohms, 330 ohms. Which resistor is going to use more of the power? That one, right? All right. Where do we look for voltage? Right here. So when it's unplugged, it's 4.95, I think. Is that what it says in the chart just below? 4.46. 4.46, that's what I said. 4.6 volts. Cool. So the car is always monitoring that circuit to make sure that it's turned on so it can detect when it's attached to an EVSE. If it's disconnected, it's 4.5 volts. That's tidy, isn't it? So what we do, we plug in EVSE. Click, click. Now my 5 volts runs out, does a little bit of VD here, comes out, keeps going, splits up, goes across this resistor. This is a good old VD. What's VD mean? That's right, voltage drop, not the other thing. Okay, if you got that, you go talk to a doctor. So it comes out, it goes to ground. But it can also go through parallel path. So it can go through here, and if S3, all this is, you ever look at the wand that plugs into the side of the car? It's got a little button on top. It's that button. If you're not pressing that button is closed. So it goes through, and it goes to ground. Is there a parallel circuit here? Damn. So now it's parallel circuit, it's lower resistance, right? Which means more of the voltage gets consumed here. This switches to how many volts? It's like 1.53. How many? 1.53. 5.52, 5.3. 1.53. Boom. Vehicle is connected, button released. That's how the car knows that it's plugged in. That's how the EVSE knows that it's plugged in. You can see both the 6 volts on the pulse width side, as well as this at 1.5 whatever. Okay? But the bottle kids, remember them? The other thing they like to do now that the trailer park's got a few electric cars, they like to go press buttons. So they walk up, they press the button on your handle. It opens this switch. If this is an open circuit, can current flow through here anymore? Nope, she's an open circuit. Now you're like, oh, now it's a series circuit. It is not. All we've done, now we've added a resistor. If we add a resistor, it increases the total resistance of that branch. If we increase the total resistance of that branch, we increase our resistance on the parallel section of the circuit after the monitor. Which means the first resistor has to consume less. So the voltage reading goes from 1.53 to 2.77. And now the car knows that somebody's pressed the button. As soon as somebody presses the button, the car is anticipating a disconnect. Thinks somebody's going to pull that thing back. So it shuts the power off right away. The charging session is complete. As soon as you pull that button, you're done. So it's plugged into level 1 or 2. Once you release the button, it'll resume charging. If you're plugged into a rapid charger and you press the button, it ends your session. Oh man, I went into a restaurant, I tried to charge up my car, somebody came along and tapped the button, I'm there for another hour. Yeah, the charger's probably going to send you a message on your phone. And if you got one of them really smart EVs, it'll send you a message on the phone that somebody stopped the charging session, but you still got to go out and resume and everything else. Most of the handles have a little tiny hole in the back of the button. It's for a luggage lock. So you can make it so people can't press the button down so you can keep charging. Cool, right? Ah, so fascinating. So fascinating. All right, so signals. Checking, check, check, check. Look at that, eh? Circuits and signals. Do you have to remember all of these different signals? No, because there's a chart there. You just have to know what circuit you're referring to, right? So if I say on a test, what voltage is present at the proximity circuit when the car is plugged in and the button released, it would be 1.53 volts, right? Yeah. So just remember that you can use the chart to look things up. But I like to get tricky. I'll ask a question like, how many volts are available at pin 5 on the EVSE side with car disconnected? How many volts are available right here on the vehicle coupler with the car disconnected? Disconnected. You got it. It's 0. Because power comes from the car, and if the EVSE isn't connected to the car, 0 on pin 5. See that? If I ask the same question, so how many volts are available on pin 4 with the vehicle disconnected, you would say 12. Make sense? Because pin 4 is the other one. Cool. All right, let's see. Level 1, 2 communications are good. This circuit does not change for level 3. Proximity is always the same. There's a little note in your book that says you can also determine the charging value of the cord. And it's true, if the cord has a resistor in it, it may change your maximum current acceptance. However, all of our chargers here have a fixed cord. The different resistor in the cord is a European standard, not a North American standard. All of our cords are hardwired, right? Everyone's okay with that? Let's keep going. Man, charging is exciting. And here we are, charging forward. Oh, we did all that. Yep, yep, that was exciting. All that, yeah, I'll do all that in a minute. That's what I want. Level 3. Oh man, we're going up. Okay, so level 3 has a couple different changes. First and foremost, the connections, look, 1, 2 for AC, 6, 7, the big balls underneath, DC, right? There's my pin 3, so that's gotta be, oh my good, what's this one, pin 3, do we remember? Oh, it's got S2, that must be my communication pilot, right? And then pin 4, proximity, no, pin 4, it's communication. Pin 3 all right. Anyone remember pin 3? It's ground, nothing major. 4, communication, 5, proximity. So control, proximity, right? Cool. Proximity functions in the exact same way. Same resistances, same values. My control pilot, though, can only negotiate up to 80 amps. 80 amps at 400 volts isn't a lot. We want to go crazy. We want a couple hundred amps on level 3. Right? Tons of power going into the battery. So we got to change our control routine. Look at that. You go here. We're still on our PWM circuit. We're still relying on switch 2 to tell us that we're connected. But we have a vehicle charge controller that has a PLC modem. And on this side, this control electronics also is a PLC modem. What happens is when you hook them up, it starts a regular pulse width. Hey man, I'm here. How you doing? Good. Not bad. You? Excellent. When we get this pulse width, there we go. So it'll come in, down, over, up, down, over, up, and it just keeps going like that. As it's doing that, the PLC modem, power line communication modem, starts looking to talk to somebody. And it does that, so if this is how many volts is that pulse width when we're plugged in and charging? 6 volts, right? So this is a 6 volt on and a 0 volt off. We're good with that? Now, what the computer does, these PLC modems, they create pulse widths on the top and the bottom, little zzz. They're communicating in the margin. So this will be 6.5 volts, this will be 5.5 volts. They got a little 1 volt signal within the margin of error for the greater pulse width. But it allows bidirectional communication. How come I need bidirectional communication? Well, if we look, off-board charger. My DC is made over here. If I'm going to introduce DC into a battery pack, does it have to be the same? Yeah, it does, right? If it's too low, power is going to flow backwards. If it's too high, I'm going to have sparks when I connect it. Right? Do I want any of these things? I don't want sparks. I don't want to put power backwards into the grid. That would be bad. Somebody would yell at me for that. Right? I've got enough people that want to yell at me. So, this communication goes in 2 directions. Where this one only goes in that direction, this PLC, bidirectional. And I can pull it low as well. So 1 volt and 0 volts. Here's my pulse in the bottom. That's how the car is talking to the off-board charger. It's inserting a signal on top of a pre-existing signal. Now, Tesla does something even cooler. Okay? Tesla doesn't need this PLC communication. PLC communication. Okay? PLC, power line communication. We'll get back to Tesla in a second. Power line communication, if you're an audiophile or a videophile or a network fan, I can send a signal through that outlet to every other outlet in the school. And it's just injecting that little pulse width on the top and the bottom of my analog circuit. So I can talk through the hydro lines. I can talk over top of another signal. 2 messages, 1 signal. Don't look up the video with 2 girls. No, don't do it, okay? Don't do it. So, Tesla does something really cool though. It starts out with pulse width, dot, 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 dot. And eventually it goes into PLC. Car goes, sup, charger. Charger goes, how much you? Car goes, do you want to talk in a secret language? And the charger goes, uh-huh. So Tesla can actually go from PLC and switch over to a 1-wire CAN network. So it can do a controller area network where it can more precisely send the signals back and forth. Most vehicles don't do that. Most vehicles communicate either PLC or pulse width on that line. And that is in order to tell this thing how many volts, how many amps. How much pressure are you going to give to the battery? If this stops talking, the charge session is over. If the car stops talking, the charge session is over. If the car draws too much, the charge session is over. The off-board charger will do loss of isolation tests on the vehicle, and if the vehicle fails, it will not start the charging process. So getting one of these things to fire off takes a few minutes. It has checks to do. Because the last thing we want is a high voltage fault in it. And you know what? I sit in this car having a good time. Let's just jam the guy with 600 volts. It'll be funny. Wait, no, that's a bad thing, right? That's a bad thing? Yeah, okay, that's a bad thing. I've just been told. So we don't do that, okay? We don't do that. Neat, huh? Again, well, this stuff, you know what? You might have to know. You don't have to know the PLC signal, but you have to recognize it. I'll show you the PLC signal tomorrow versus a car that doesn't use a PLC signal. Okay. The last thing I really want to go over today, because we're running out of time and we only got through charging systems today, we'll have to do climate in the shop. Ooh, no! You'll be okay. right? We'll explore some stuff and we'll actually do some theory down there. But the last thing I want to do is, oh, no, not that. We got to get charging connections done. So right now, we've got, who's that? J1772. And it can do, what levels can it do?
1, 2.
L1, L2. We get J1772. Hey, little fellow, we got to draw his dimples again. But we add 2 terminals underneath. There we go. What's this called?
CCS1.
CCS1. And it can do level 1, level 2, level 3. If you use that on a truck, what level does it do? Just level 3. Right? The fleet stuff. If you got a fire truck, if you bring your fire truck back to the fire station, electric fire trucks, we actually have them. Toronto has one, pretty good one. Brampton has one, not so good. Shh, don't tell anybody, okay? We definitely will post this to a major social media platform. Right? But those trucks, they come back. I want Brampton's battery powered. That's it. That's it. Do we want to take several days to recharge that truck, or do we want to do it fast? We probably want to do it fast every time. York Region has electric ambulances. Fast, or just take our time recharging those? Fast, right? So why add an onboard charger? CCS1. So if we go industry, possible, L3 only. Bam, just like that, okay? All they do, they take these 2 pins out. The blanks are there, but there's no metal inside. Yeah, CP is there, PP is there, and ground is still all there. Okay, just stop 2 pins. So we get that, then we get all excited and we go, let's join the future. We get this guy. The future is supercharged. Is that what you just said? Yeah, kind of, yeah. And the future looks like a mad clown face. I don't even know if I did it well. Let me see. Close enough. Close enough, right? The 3 pins should be on the same level. What is that guy there? You can see it in your book, right? It's right beside CCS1. It is supercharged. Okay, so we got supercharged. Supercharger. What else do we know it as? The Tesla charge connection, right? And then Elon, because Elon is Elon, said it's the North American Charging Standard, or the NACS, or, well, since he opened the patent when he said it's North American Charging Standard, now the SAE got their hands on it, and it is the J3400. Lots of names, same plug. Why do we care about something so proprietary? Because the patent is open. And that plug works better than CCS1. Remember that button that I told you about? Where if you press it on the handle, it says, eh. The Tesla connector, once you lock the car, it tells the connector to lock. And it's an electronic button on the handle. So if you don't have the key fob in your pocket, you press that, it doesn't let go. That's pretty good, right? So it's got security to it. The cable for that thing when you're supercharging at super high rates is probably smaller than my thumb in diameter. How does that move around in the wintertime? Pretty good, right? Pretty flexible. The CCS1 cable is about that big around. You feel like a Ghostbuster trying to put that thing in. as you plug it into a plastic socket on the side of the car in the middle of winter. Ooh, scary. Plus, the NACS connection can handle more current. What levels is it capable of, you say? Well, if you look, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. The NACS uses the same communications as the J1772. But this guy, watch this. This guy is neutral, L2, or DC, it's in your book, it's either positive or negative, okay? The other side, and it's capable because they have pupils. The inner pin is a different current than the outer pin. The other side is L1 or a DC connection. So this guy integrates the DC connections into a smaller head. That's pretty handy, isn't it? That's pretty handy. Let's ask the hard questions. Are we ready for the hard questions? You're ready for the hard questions, I can tell. All right, here's a hard question. So, what levels? Level 1, level 2, level 3. This charger, with a much smaller surface area, can do everything that the CCS1 can do, and it does it a little bit better. So since that patent's available, do you think anybody wants to use it? My Bolt is a 2022, it's got CCS1. If you're going to buy 2027, it's got an NACS connector. So Ford, they say they're switching over to NACS. Hyundai, NACS. We are going to see the wide adoption of this Tesla protocol because it is better. It is honestly a better connection. And it hurts me to say that, right? Oh, his engineers are good. Ugh. So, let's talk about Japan though. Who likes Japan? I'd love to go to Japan. I've been exploring Japan in a digital format for the last 2 weeks, okay? And then before that, ancient Japan for many months. Digital formats though, okay? Neat stuff. But, back when I was working for Nissan, we brought the Leaf over to North America. We brought the Leaf over to North America before CCS1 was widely adopted. We had J1772. J1772 is good for level 1 and level 2, but the Leaf is a fully electric car. And the very first generation Leaf, the range was less than desirable. So you have to charge it rapidly, right? Well, I didn't have a CCS1, I didn't have access to the Tesla charger, all I had was a J1772. I had to find a way to make the car charge faster. There's another connection that I didn't show you, or embarrassed about it. Okay, it looks kind of like this. I'm sure you can make an anime character on that. No, we don't get pointy eyes on this one. It's just like that, okay? This guy, C-H-A-D-E-M-O. I think the D's big. I wrote it properly in your book if you have it. If I, what's that? It's capital A? Okay. Oh, there we go. I knew something was wrong. There we go. Chad DeMo. Chad DeMo has got 2 big pins on either side. Chad DeMo is only capable of level 3. It can't do level 1 or 2. It is a completely different socket, and it talks in a completely different way. CHAdeMO does not use any of the protocols that I just told you about. It uses its own specific So it's got ON CAN, and it's a 2-wire CAN. So it's a traditional controller area network protocol. How easy would an adapter be between CHAdeMO and CCS1 connections? They don't talk to each other. The language is different. You need a powered adapter. Ooh, how easy is a Tesla to CCS1 adapter? Simple, you plug the wires in. Easy, easy, right? So hard to adapt. Specific proprietary plug. You have to have a wider surface area to put these plugs into. Oh man. Right? I have a car downstairs with a CHAdeMO on it. We can look at it. You pop the front of the car open and there's 2 plugs. There's a J1772 and a CHAdeMO right beside it. Isn't that neat? So one charging protocol for level 1, 2, another one for level 3. If you're out and about driving one of these cars, you have to find a charger with a CHAdeMO connection. What does CHAdeMO stand for? What does CHAdeMO mean? So where did it come from? It's a Japanese-French standard. My guess, since they like to share contribution, I bet you it came through Nissan Renault, would be my guess. Okay? That's a guess, however. They call it a Japanese-French standard. And what the name implies, charge de move. CHAdeMO, charge de move. That's what it means. Weird little connector, going the way of the dodo. What happened to the dodo? It's extinct, dead, right? Nissan with the new Leaf did not put this connector on it. I think the Aria got rid of it. And they're either CCS1 or NACS. Why would I put a J1772 alone, all by itself on a car? What kind of car would I put that on? Why not just make it a CCS1? Right? If I have a plug-in hybrid vehicle and I run out of battery power, am I stuck? Nope. Gas engine fires up and it drives the car. Charging at level 3, introducing that much current into a battery creates a bunch of heat. Heat kills batteries, true? Do I need to abuse the battery if I have a plug-in hybrid vehicle? No. So there's no need to install all the devices required for level 3 charging on a plug-in hybrid. Easy peasy. If I take that Prius home and I plug it into my level 2 charger, it goes from 0 battery to 20% battery, all the way to full battery in 2 hours. Do I need a rapid charger? Not at all, right? If I plug it into level 1, it goes from 0 to full in 4 hours, because the battery's little, right? 10 kilowatts. So level 3 is a road trip charger, something to use when you have to extend your journey. They're expensive to use. If I plug in just at my house, it's about $80 a month on electricity. If I use a rapid charger for an hour for my car, it's somewhere between 30 and 40 bucks. And all of a sudden I'm paying the same as I would for gasoline. And nobody likes that. Ew. Right? So, that's our different charging connections. You okay with these? So far? Okay, I suggest reviewing this chapter because there's a lot of technical, weird stuff that goes on. Okay? So, we did that, we did charger operation, we did signals, climate, no, we're not doing that. There we go, we got this done, and finally, I'm gonna go back, I'm not even gonna draw for you on this one. I should, but I'm not going to, I'm lazy. Ready for it? Not that, this. Okay. Whoa, what's going on in here? So, inside of your onboard charger, there's a DC to DC converter, right? Because we took wall AC, remember that? Turned it into DC, turned it back into AC, used an electromagnet to step the voltage up, then cleaned it, rectified it, turned it back to high voltage DC, and sent it out to the battery. Remember that? That's a DC to DC converter. We also use a DC to DC converter instead of an alternator. So there's one in the inverter, and there's one to charge the low voltage battery, or the auxiliary battery. How do they work becomes the question. So, one side of our DC to DC converter is going to be hooked HV positive, and way down here, I'm going to draw a line kind of like that, HV negative. High voltage bus is going to come into our DC to DC converter. Are we okay with this in theory? All right. Up at the top, always, 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 always. Conventionally speaking, it is DC traveling in that direction. True? And at the bottom, it is DC traveling in this direction. And what are these guys right here? I drew this myself. They're IGBTs, or MOSFETs, depending on the situation. Basically, they're electrical switches. They're either open or closed electrically. We're okay with this? All right, so we are going to alternate the way that we are opening and closing the switches. We are going to make pairs. Ooh, I like pink and purple. Pink and purple, I hope it shows up. So, for argument's sake, that is a pair. But they're on different lines, sir. I think you're drunk. No, it's okay. And this is a pair. You know what? We'll change the color. Pink and purple might not be the play here. Pink and green. That's the play. All right, pink and green. And then these two are also great. Oh, that was the play. Look at the contrast there. Can you imagine if someone decided to dress in pink and green? Ew. Purple and green? The Joker? Yeah, that's all right by me. All right, so if I open these two, let's see what happens. So, get some power flow. Comes from here, got to go through there, goes down here, and it hits this splice. Can it get through here? These are open. This one's closed and that one's closed. Can it get through there? Nope, open circuit. So it's going to hang a bit of a right-hander there. It's going to go through. And it goes through the coil. What's that do in the coil? What does current flow through a coil do? Makes magnets, right? So, let's say if it goes through this way, we can actually use the right-hand rule, but we don't know the actual winding of this. We'll say this is the North Pole, and this is the South Pole. You good with that? And then it goes through, goes that way, and back to the battery, right? We're doing the DC thing, it's going this way, came in that way. So I got a magnet, it grew. Now I gotta turn it off and switch direction. So what I'm gonna do to turn it off, I open these circuits, and to switch the direction, I close those ones. Well, what does that do, you say? Well, it comes through, there we go, right through here. It can't exit through this open, it's gotta go through this closed one. So, go this way. Look, the current goes in the other direction. If it goes in the other direction, that means that we've made a north pole and current flows that way, and a south pole when it flows the other way. So this goes through, goes through here, and goodness. Is it DC here? Yeah. Is it DC here? Yep. Right, flows out one direction, flows in one direction. Is it DC in this coil? No, sure is AC, right? So, step 1, HVDC to HVAC. And that happened right there. How do I control how much AC that I have? How do I control how quickly and how big that magnet gets? How quickly do I switch these back and forth? How long do I leave them open for? Pulse width modulation and oscillation, or changing which gates are open and which gates are closed. So forward, backward, forward, backward, forward, backward, forward, backward. Forward! Really hard or really soft? Well, all the switching and the amount of magnetism allowed through will change the output. So how is the output controlled? By switching transistors on the high side. How is output controlled? By switching transistors on the high side. I have a video of this where it's actually big on the screen. I'll put it up as well, okay? So, we're switching. It's creating a magnetic field. Magnetic field in this one, you know what? Good call, we'll make purple. So we've got a super duty magnetic field. It's purple. It's going in 2 directions. It's got big waves. Those waves are crashing against a conductor. If I move a magnetic field back and forth across a conductor, what happens? If I move magnetic field back and forth across a coil, what happens? Yeah, that's what the magnetic field does. What does it do to the conductor?
Increase and decrease. Switches.
Switches what?
Polarity.
No. So I made it in one conductor and I'm shoving this magnetic field back and forth over the other one. That's how I do regen braking. Move a magnetic field back and forth across a conductor. That's how I do an alternator. Move a magnetic field back and forth across a conductor. What are the outputs of a generator? What are the outputs of an alternator? I can show you. What's that right there? Old man fat, that's what that is. But it represents power, right? Power! Yes? What type of power? No! Magnet across a conductor makes electricity. Done. A moving magnetic field across a conductor causes current to flow. Take it, stick it in the back, save that. You know how in the Matrix, you know Kung Fu? That's an old movie now. Now you know moving magnetic fields across a conductor create current flow. Create electrical potential. It's voltage, right? If I have more coils in the secondary side, I get more voltage. If I have less coils in the secondary side, I get less voltage. So I'm creating AC current in the secondary side. Let's see, what does that look like? Wrong colors, man. There's the right colors. So, as we create this excitement with our magnetic field, we get AC current. True story? So, step 2. In this one, HVAC, and we're going to call this a DC to DC converter, and we're going to call this a 12-volt battery. Is everyone okay with this being a 12-volt battery? So do I want high voltage or low voltage? Low voltage, right? So high voltage AC to low voltage AC. Nailed it. Cool. All right, so now I've got this. Could it flow backwards to the battery? You're going to say, well, sure it could. No, it can't. Let me tell you why it can't. Okay? It can't flow backwards to battery. Don't worry about the contactors. There's nothing in this DC to DC converter for contactors. If it's flowing backwards, it's got to pull current out of the positive. There's diodes here to stop it from flowing backwards. So, as it excites this coil, it can only flow either this way, through that diode, or this way, through that diode. Once they converge here, at the splice, right after the diodes, is the AC traveling in the same direction? See how this one goes this way, that one goes this way? Once they hit here, which way do they go? Can't go that way, can't go that way, so they must both go in the same direction, right? They become low voltage DC again, right? Low voltage DC again. So step 3, low voltage AC goes into low voltage DC. Man, 3 steps in a DC to DC converter. Pretty good. Once I have low voltage DC, let's say it's 13 volts or 14 volts, it's ready to charge the battery, can I just send it out as is? No. Because once I rectify from AC, right? So AC is like, here's my midline here, and AC kind of looks like this, right? That symbol looks familiar, doesn't it? AC sine wave. Well, once I rectify it, all I've done is I've chopped the bottom off of it, and it's going to look like this. What would a signal like that do to my DC circuit? Oh, my lights would be bright and dim and bright and dim. My stereo would go vroom, vroom, vroom. Would we have fun with that? We can't have that ripple inside of a DC circuit. So I got to get rid of the ripple. I got to filter. I'm going to filter it in 2 ways. This guy here, it looks like that guy there, doesn't it? Looks like a coil, doesn't it? Yeah, but that coil has a new name. That coil is called a choke. That choke is going to stop AC voltage that might have been still unfiltered from getting in. It's called an inductive load. Right? It's an inductive coil. We're going to call it a choke, and its job is to stop wayward AC. Remember that. Put it right there. Okay? And then we got another guy. So this won't have any weird jank to it, right? We don't want any of that in our DC. And if we have real DC, nice clean stuff, we don't want it to all of a sudden go, that'd be bad, right? That's what the choke's for. To get rid of the ripple, though, we need it nice and smooth. So we use a whole bunch of these. Do we know that symbol? We can add another one. And another one. I can just keep adding them. You can use that symbol or this symbol here. What are they? Capacitors. Okay. As we create current, as we create voltage, we're not creating this nice smooth 13 volts. We're creating 16 and 9 and 16 and 2 or whatever it might be, right? We got peaks and valleys. What the capacitors do, when it's way up here, they take in potential energy. So they cut the tops off all these. And then when the energy falls down, can capacitors give back energy really quickly? Sure they do. So they take the peaks, they take all that potential energy, and when the voltage falls down, they throw it back out. So when they throw it back out, it takes off all the valleys. What we're left in is this, get out of here, super smooth line after all this filtration. So that DC to DC converter, 4 auxiliary batteries, takes high voltage, it turns it into AC, it induces low voltage, turns the AC that was induced into DC, and then filters it and fills the battery with that. If we're trying to charge a high voltage battery through the onboard charger, it has a DC to DC converter in it. You can see the coils of it, right? It sits between, here I'm just gonna go back. There it is, the voltage converter and the rectifier. There it is, that little fella, it's right there. But instead of going down, this guy goes high voltage DC, high voltage AC, higher voltage AC, higher voltage DC. So this is a boost converter. The one for your 12 volt is a buck converter, brings it down. So you can go up or down, and you can get DC to DC converters that can do both. Those are known as boost and buck converters, not widely used anymore. All right, look at that, isn't that fascinating? I love this. This stuff is like, put it in my veins. Speaking of veins, it's time to fill the tank and get out of here. 11:53, what else did you want to learn today? I have this funny feeling that 3.5 hours of theory are more than enough for most people. Anybody want more? You guys are packing. All right, I'll see you tomorrow. We'll be in the lab, F110, and I'll have some stuff set up. We'll look at some of these signals tomorrow. I'll have the back of the photos out for us. You should be able to see some cool signals back there. Okay? And we're going to do a shutdown on the Chevrolet Bolt tomorrow. Remember I showed you that question, how do you shut down the Chevrolet Bolt, and I took it off the test? Nobody knew. You know how you guys have all been taught the only way to shut something down is with that manual service disconnect? People like to lie, you know that? Let's discover a different way, a better way, together. But until then, let's be a part. Have a great afternoon.